like what does this matrix do? This matrix P is going to project and any other vectors on the column space of X. Okay, so for example, let's say that this plane is the column space of X. Okay. Now there's another vector go this way. Let's take it as the 3-dimension. Okay. Now we are in the 3-dimension world. Okay. So once we time that vectors with the projection matrix P, it's going to project. So just imagine that you have a light over here. Okay, it's going to, the shadows of these vectors is going to be on the plane here. Okay, so once you time this projection matrix, it's going to have the correspondent vectors here. This is P times Y, which is after you multiply by this projection matrix, and it's going to light on the plane exactly. Okay. Okay, so that is the idea of projection matrix. Okay, and it has some like interesting property. You can do it by try to verify it by yourself. It's called the idempotent, meaning that you multiply it by itself twice, and you will still get the same stuff. Okay. And if you transpose it, you still get the same result. Okay. Now we are going to look at the linear regression models, which is kind of jumpy here, but I'm going to talk about what is the relationship between these two concepts. So in a linear regression model, or like OLS, if you like have heard of it. So it's like this one. Big Y equals to X times beta plus epsilon. And you can write down in a matrix way, Y1 to, for example, like Yn. We'll have a lot of covariance here. This look like this one. X1, 1, X1, 2. Okay, and K. Okay, so this is the linear regressions model. Okay, it's kind of like now I tell you all the characteristic of certain subject. For example, like let me see. So let's say that we are interested in your income, and you may control for example like the how many years you are in school, and your work experience, such and such and such. And we want to know how good we can use those characteristics to approximate and get the result that is getting closer to the object of interest here. And of course, there are some error turns in the end because it's not going to be perfect, right? So if we look at, so that basically that is how regression model is. And now I want you to take that as the linear algebra. Okay, so what is this part? So this is the multiplication of one matrix big X here with with beta. So that is actually the linear combination of all the columns of X, right? And why is that exactly? If I tell you that you can use whatever beta you want, then that is the column space of it, right? Because if now I can put whatever beta here, that means that actually is the collection of all possible linear combinations of the columns, all the column space of X. Okay. Once again, so now if I give you a certain beta here, says that, okay, so beta 1 equals to 1, beta 2 equals to, for example, 3, etc., etc. If I give you exactly numbers here, I fix that vectors and you multiply it, then you will get linear combinations of all the columns of X, right? If this is variable, you can change whatever to whatever numbers you like. Then that's actually give you the column space of this X, right? Okay. Then back to this graph. So that is exactly what I mentioned there. So this is the space that spanned by all the vectors in this X. Okay, and what is the OLS wants, or what is our final goal? Our final goal is to find a specific vectors in this plane such that it minimizes the distance between y hat, which is the vectors on this plane, and the real y here. Okay. Get it? Because we have so many choices. Now I give you the whole X, and I can spend the column space here. That means for each vectors on this plane is available to you, then which one you are going to pick? You are going to pick that vectors which has the closest distance to the y here, which is something you want to predict, and you want to make the prediction error as small as possible. Okay, so that is the idea. Therefore, we already know that what is this? This is the vectors that after you multiply it by the projection matrix, because this is going to directly give you the closest vectors on the plane spanned by the column vectors here, and you will automatically get the smallest distance. Okay, so that is the idea, and this is how you operate. Okay, so this y hat on that plane will equals to p times y. Okay, and hence you can directly get the p hat, which is the estimation of that beta will equals to this after some rearrangement of your of that equations there, and at the same time you will get the residuals here. Okay, that is the idea. Okay, so that's one application of projection matrix. And of course, if you say that, okay, so it's too abstract to me, then another way to get the result is to use the derivative. Okay, so this is how the derivative works out, and then we go back to see our original problem here. Okay, so our goal is to find out a specific beta that will give you this y hat here. Okay, and the goal or the criteria is to minimize the distance between the real y and the y hat, which is x times beta over there. Okay, so that is our objective functions, and we are going to what can be changed is the beta. So we are going to find the exactly beta that can minimize the distance. Okay, so you just kind of expand it and rearrange it. You will get the objective function look like this one, and take the first order conditions here and rearrange it. Then you can still get